Okay. Hi everyone. I am Feline Zhao, and I today I'm going to talk about application of intermolecular forces. And let me just share my screen really quick. Let's see. Okay, here we go. Okay, so applications of intermolecular forces. So the things we're going to talk about today is solubility, surface tension, adhesion and cohesion, capillary action, viscosity, volatility, vapor pressure, and boiling point. So to start it off, we're going to talk about the concept of solvent and solute. So the solute is a substance that dissolves in a solvent, and the solvent is a substance that the solute dissolves in, which has the most moles in the whole solution. So basically, here's an example: is hot cocoa, because yesterday I was really sick and my roommate brought me hot cocoa, and I thought it's a great example. So what she did was she basically mixed cocoa powder and sugar, like the hot cocoa packet, with milk. So in this case, the cocoa powder and the sugar would be the solute, and the milk would be the solvent, because the cocoa powder is the less mole and the milk is the more has the greater majority of moles in the solution. So I thought that was a fun example. So now we can talk about solubility. And in solubility, we always hear like dissolves like. And that means polar dissolves in polar, non-polar dissolves in non-polar because of the similarities in intermolecular forces. So solubility, it depends on the solute-solvent interactions in relation to the solute-solute and the solvent-solvent interactions. So you think about it, you can think about as we have a circle, and the circle is like the solute, and then their surroundings is solvent. So the interactions between the circle, everyone's holding hands together, that interaction in relations to like the interactions to the solvent, kind of trying to attack and try to kind of disturb that. You can think about in that concept. And there's a trend in solubility, and that trend being it decreases with longer chains, and that is because intermolecular forces increase. Um, when intermolecular forces increase, it makes it harder to break the bonds. So solubility thus will decrease because the chains are longer. So now we can talk about surface tension. So surface tension is the tension the surface of a liquid contains due to intermolecular forces. So you think about it, I think we did this lab before. You have a penny and you just drop water droplets onto the penny and you see how many droplets. I think when we did it, I think it was around 25-ish droplets that we did, which was pretty amazing. And so the trends in surface tension is the greater intermolecular forces, the greater the surface tension. So when we did the penny, we did water and oil. And from the results of the experiment, we found that the penny could fit more water droplets than it could fit the amount of oil droplets. And that is caused by water having a greater intermolecular forces because contains hydrogen bonding, whereas oil only contains nonpolar London dispersion forces. So that is a example of this trend in surface tension that is helpful for me to think about. Next is adhesion and cohesion. So adhesion forces are attraction between like molecules. So for example, liquid and liquid. And cohesion forces are attraction between unlike molecules, so like the bottom liquid. An example of this would be if I have a test tube and I have water. So the water molecules binding together, that would be cohesion. And the water molecules binding to the bottle, the test tube, that would be adhesion. And I found this really cute picture. I credit it. It's from Bio Ninja. I love the name. So basically, these two water molecules are holding hands because they're trying to bind to each other, so they're not letting go, and that is cohesion. And also, they're also getting pulled by attraction between the whatever material is, say like glass or something like that. It's also getting pulled that way. So it's constantly having that attraction between the molecules and outside the molecules. So this is a cool picture that is really helpful to look at. So we have a second slide of adhesion and cohesion, and this one is when we think about doing a test tube. We learned that sometimes, water has this meniscus. And for water, it is called concave meniscus because it goes down. And when we read the test tube, we read like the bottom line of the meniscus. That's our volume. So, and that meniscus is caused by the adhesive forces being greater than the cohesive forces. Um, so you think about it, it's because it's climbing up. It has this round thingy. It's because the adhesion forces, which is the force of the liquid and the bottle, is greater. That means it's climbing up further up there. So it's like pulling it further up there. Whereas the cohesive force is a little less strong. So it's kind of getting dragged along as the adhesive forces kind of pull the water, like kind of attract the water to the side of the glass. So whereas mercury, we find this convex meniscus, and that is when the arch goes up instead of going down like water does. And that is the exact opposite of water, and that is caused by cohesive forces being greater than adhesive forces. So that's the same concept. So you think about it as the cohesive forces being stronger, that means it's binded more tightly together. That was harder to break apart. It's harder to kind of pull apart and like pull it up there. So when the cohesive force is stronger, the molecules bind together greater than how the molecules bind to the glass, which means that the molecules are going to be more concentrated. They're going to be tighter to each other in the middle where all the liquid is going to be. So that's why we get this convex meniscus that arches up instead of arching down. Okay, so now we got capillary action. So capillary action is defined as the ability for liquid to go against gravity spontaneously up a tube. So capillary action is usually, you see this little tube thingy and there's nothing, no energy input into it, but the water just like goes up. It's actually so cool. So there's a trend in capillary action. It's the bigger the molecule, the slower it moves up a table. It's because if you think about it, it's bigger, so it's harder, it's less flexible, it's less mobile to climb up to like higher places because the mass is bigger. And the water, it moves up because cohesive forces is smaller than adhesive forces. Like we talked about, the cohesive forces is between the liquid and the adhesive forces is between the liquid and the glass. So it moves up is because the adhesive forces, it's stronger, so the liquid is binding more to the material, say like glass or just a plastic tube or something like that. So it can cause it to keep climbing up using that attraction between the liquid and the material. So that is why water can climb up a tube without, say, people blowing on it. It's because of that attraction. Okay, so next we got viscosity. And viscosity is resistance to flow. And you can think about it as the stickiness. So I think about molasses, honey, anything that's sticky, or like syrup that's just sugar. But anyways, there's a trend for viscosity, and it is the stronger the intermolecular forces, the higher the viscosity. And you think about it, it actually would make sense, is because since the intermolecular forces are stronger, they are pulled tighter together. So the density, with the way I think about it, was because they're pulled tighter together that it's hard to break them apart. It's harder to let them be more fluid and be more easy to shape. So there are other factors that goes into determining viscosity, and we got molecular shapes. And that one is the longer the molecular shape is, the more viscous it is going to be. And then we also got molecular size, which is the bigger the molecule is, the more viscous. So since the molecule is bigger, the increase of intermolecular forces, and it's just going to be harder to be more fluid and be more easy to move around. And we also got temperature, and colder is more viscous. So you think about it, I have a picture of a honey right here. When honey jars kind of harden, what you would do is I would do is I put it in hot water and like let it kind of get more runny so I can actually pour it out. So that's a great example of temperature being affecting viscosity, is because when you think about it, when honey kind of solidifies, it's usually at room temperature or colder than room temperature. So that means it's more viscous because it's more sticky. It's harder to move around. But when you heat up the temperature, when you heat it to a point where it's going to get kind of start melting, breaking that intermolecular force, kind of just being more fluid, that's when it becomes less viscous. So the way I remember viscous, I just remember it as stickiness. That usually helps a lot, just to visualize. Like I think about honey, I think about just like anything that's sugar and sticky. Yeah. So now we have volatility. And volatility is the tendency of a substance to vaporize. And we have a trend in volatility, and that is the stronger the intermolecular force is, the lower the volatility. So volatility is a little different than, so you think about other trends. We got solubility, we got, oh, my mind is blanking out. Okay, we got solubility, we got viscosity, and that kind of stuff that has a trend of higher intermolecular forces, higher, say, like viscosity, for example. This one's just a little different. It's because volatility is tendency of a substance to vaporize. And the reason why stronger intermolecular forces have a lower volatility is because when the molecule has a weaker intermolecular force, it contains more gas particles. So it's easier to vaporize, and it just has more gas particles, and it has a higher vapor pressure. So because it's such a weak intermolecular force that like they can vaporize really easily, say like hydrogen, for example, it vaporizes really fast. So, and it doesn't have a very strong intermolecular force. So that's why volatility has this trend of stronger intermolecular force, which means lower volatility, is because it's not stronger intermolecular forces makes the substance not as easy to vaporize. So it's a little bit different of a mindset to think about. And it's just a little different than the other concepts that was covered. So now we can talk about vapor pressure. So vapor pressure is the pressure exerted by the vapor over the liquid in a closed container when it is in equilibrium. So we talk about trends in vapor pressure, and it is the weaker the intermolecular forces, the higher the vapor pressure. And that is because, wait, oh my gosh, my mind's like blanking out. I'm so sorry. The weaker intermolecular forces, because when it has a weaker intermolecular force, it vaporizes more easily. So that can relate to volatility when we talk about weaker intermolecular forces having a higher volatility. So basically, when it has a weaker intermolecular forces, it has a higher vapor pressure because the molecules tend to vaporize more easily, creating more gas particles and increasing the vapor pressure. So the last thing, the last thing we're going to talk about is boiling point. So boiling point is, we have a trend of boiling point, and as the larger the molecules, the stronger the intermolecular forces usually have higher boiling points. So I have a table here, a chart that is really helpful when you look at it. So we have C5H12, and let's find the London dispersion one. We got, let's see, C5H12. This one is just another isomer. So when we say that, so more branching, we talked about this when we talked about intermolecular forces. So London dispersion forces, as the chain gets longer, the forces get stronger, and with less branching, the forces are stronger as well. So when we think about it, the first C5H12 that is more linear, has a stronger London dispersion force than the second C5H12, which has a little branching that's going on. So as we can see, the boiling point is 36 degrees Celsius, whereas the boiling point of the second one is only 28 degrees Celsius. Next, we can find we can find another example of London dispersion. We can even look at these two. This one has a little bit, the C5H12 that has one branching. I'm not sure if you can see my mouse, so I'm gonna have to describe it. So the first C5H12 that has a branching exhibit a higher London dispersion force than the second one that is basically like a cross shape, which has more branching. So that means the London dispersion force of the one that has more branching that looks like a cross is lower than the one that only has one branch going on. So thus, the boiling point of the first one is higher than the boiling point of the second one. The one with the only one branch is higher than the one with two branches, so the one that looks like a cross. So that's how we can think about that. And also we can look at the size of the molecule. So we can look at, let's say, this C5H12 and CH4. So they both are kind of like a cross-shaped, at least the carbons and the carbons in the C5H12 and carbon hydrogen in the CH4. So basically, when we think about it, is that the C5H12 obviously is bigger, has a higher molar mass than CH4. Thus, we can see that C5H12 has a boiling point of 10 degrees Celsius, whereas CH4 methane only is like so much lower. It's negative 161 degrees Celsius. So we can really see the difference when we look at these in comparison, like in a table, we can visualize it. So I think that is all I have today. I hope that this can help you in solving some of your unanswered, like some concepts you might be confused about, like these examples of hot cocoa, honey, like these pictures can help you visualize like these trends and why they exist. So I hope this can help, and I wish you guys good luck on your final exam. Thank you.